Hi, everyone. Are you ready for some mechanisms? Oh my goodness. We're going to take a look at acid chloride reactions and the anhydride reactions. I'm just going to knock down all these mechanisms. Now, maybe I'm putting too much emphasis on it. It's the same mechanism. It's just going to repeat with different reagents. So watch for the patterns and just make the modifications depending on which reagent you're using. So it's pretty straightforward. But I know it gets a little bit repetitious, but hang in there. Okay, so what we got? We're in Key Concepts, Unit 3, Part 3. We got acid chlorides, the first of our carboxylic acid derivatives. There we go. Yeah, that's what it says right here, nucleophilic acyl substitution reactions. That's the category for all these reactions. And the pattern is going to be, we're going to bump up the pi bond, and it's going to come right back down. It might not be immediately, but somewhere in the mechanism, that's going to be the pattern. All right, so first one on our list today is hydrolysis. That's using water. And it could be acid catalyzed or base catalyzed. However, as we saw in the previous video, acid chlorides are the most reactive of the derivatives of carboxylic acid. So you don't need a catalyst. Now, so we'll get all three variations here. Acid chloride. And I'll squeeze it in here. I want to see them all on the same page. Acid chloride. And you can react with just water. You can react with hydronium. You can react with basic water. Water at pH above pH 7. So just neutral water, acid catalyzed, base catalyzed, and you get carboxylic acids out of all those. Okay. Yeah, this is not a reaction that you want to use for synthesis because there are much easier ways of making carboxylic acid, like from a primary alcohol, right? Just use potassium permanganate or some other strong oxidizing agent to take a primary alcohol to your carboxylic acid. Yeah, so this is not a useful reaction, but it is important, especially if you're in the lab and you have a bottle of acid chloride and you open up the top. The fumes might come out and you actually can see a little cloud forming. It's like, whoa, keep that away from you. What's going on there? The reaction's actually happening right in the air. And if you inhale it, the reaction can happen in your nose. So no, don't be doing this. Keep that in the fume hood. Right here, let's go through the mechanism because it's just going to be one of many of the same pattern. Okay, so we got our acid chloride. Let's just take the simplest one, but they all work. Acid catalyzed or base catalyzed, take the water molecule, oxygen with a lone pair. That's a weak nucleophile. And you might remember when we hydrolyze amide aldehydes and ketones, you needed an acid catalyst or you needed a base catalyst because water was just too weak to attack the aldehyde or ketone by itself. Not the acid chloride. Acid chlorides are very reactive in water. As weak of a nucleophile it is, acid chloride says, come on in. I'm ready to react. Bump up the pi bond in step one of the mechanism. So now the oxygen that used to be double bonded is negatively charged. Water keeps all its hydrogens in step one of the mechanism. Step two, bring that pi bond right back. And then kick out the weakest bond, the most stable leaving group. Okay, so sometimes the water does depart because that is a nice leaving group. Water is very, very stable. So this bond can break right here, but sometimes it's this bond. When the water breaks, you actually make this first step reversible. Water comes off, you reform the acid chloride, and it has to try again. On the exam, you don't need this double arrow, but it is something that happens. Okay, to move on to the final product though, pi bond reforms and the chloride leaves. Nature says, yeah, that's a good choice too, because chloride ions are not bases. They're very stable. And the last step then, you got to bring in a second water molecule to serve as a base to remove this extra hydrogen. There we go. That's the mechanism. And again, we're going to have some, that's what this video is all about. We're going to bring in some nucleophile, somebody with a lone pair, and they're going to bump up the pi bond. Pi bond comes back down. There'll be a cleanup step to get to a stable product. Okay, so if we choose water, we do hydrolysis, and we make a carboxylic acid. But we could choose an alcohol. No, we're going to choose the anion. There it is, right here. We're going to choose the anion of a carboxylic acid. So start with the acid chloride. The reagent is going to be the anion of a carboxylic acid, and usually have a counterion there. But sometimes you might just write O minus the anion of carboxylic acid. And we're going to do substitution, nucleophilic acyl substitution reactions. That's this video. And you're going to substitute the O with all of its carbons and all the groups with the chlorine. So take the acid chloride, chlorine comes off, the rest of the molecule goes on, the rest of the reagent goes on. So we got an O with the double bond O, O with a double bond O, and in this molecule, there's a methyl. Ooh, and that's an acid anhydride. That's how you can make them. If you decide to have a methyl over here and over here, you put something else, then you get that something over here. And now the anhydride is unsymmetrical. These are sometimes called a mixed anhydride. And this is a good way of making them. So oftentimes, our anhydrides will have the same set of carbons on both sides of the anhydride. That's a symmetrical anhydride. And they're the most common ones. But if you want a mixed anhydride, this is a good way of doing it. Memorize the mechanism. Well, just apply the mechanism we just had with the hydrolysis of acid chlorides. Negative oxygen, or somebody with a lone pair, that's our nucleophile. Hey, go bump up the pi bond. Done. That's step one. And then let's put the chlorine down here. Whoa, where did that pi? Why is that pi bond there? 5 bonds of carbon? I don't think so. I'm gonna put the chlorine down here. So here's what remains of the acid chloride, and then attach this oxygen to this sp2 carbon, and we're gonna get the tetrahedral intermediate. I forgot to point that out in the previous mechanism. Not a big deal. When you have to draw mechanisms, you're just drawing the structures and the curved arrows. You don't have to label it with words. Okay, that's the end of step 2. That's a product of step 1, I should say. What's the next step? Bring back the pi bond. A lone pair, you go right back down there, and then this carbon says, okay, do I want to let go of this carbon, make it negative? No. Negatively charged carbon is not electronegative. It's a powerful base, very unstable. Nature says no to that. Okay, maybe we break this bond, release the chlorine. And the answer is yeah, we can do that. So pi bond came back down. The oxygen with this double bond O, the other carbonyl group, stays there. And you have your mixed no, that's not mixed. You have your anhydride. And then, like I said, with the hydrolysis mechanism, sometimes this bond will break. And that just means you reform the acid chloride and goes back and forth. We have an equilibrium step here. That's kind of nice. I don't know. It looks weird because this has a lot of atoms and there's no oxygen. That's a distraction. But if you compare this mechanism to the previous one, slide up or rewind the video, they're exactly the same. It's really the same mechanism. Synthesis of esters. What do you think this mechanism might look like? Yeah, pretty much the same thing. It's a little different at the end because now, well, let's draw it before we start talking about. I'm going to start with the acid chloride. And then what do we want? We want an ester. Oh, wait, that's not how we're going to format it usually. You can. Usually we have the arrow right here. Sorry. So what's an ester? It's the C double bond O carbonyl group with an ether-like oxygen, and then it has some carbons. I'll put 2 over there. So then what's missing as you start with acid chloride, you go to ester, it's missing the O with that. Okay. The simplest form of ethyl with an oxygen is to have a hydrogen here. So you simply have an alcohol. Okay. It is true the alcohol is a weak nucleophile, but acid chloride is very reactive. You can get it started. The lone pair on the alcohol will bump up the pi bond, but it's this hydrogen that needs some help being removed. And we need another base to come in here. So we want a base that's not going to make a new product with the acid chloride. And pyridine fits the bill. Pyridine is a mild base. It's sometimes called an acid scavenger. Because its purpose is to scavenge or to pick up any loose H pluses, any acid floating around. Because if you don't add that base, the yields are really low. The acid stops the reaction. So put a little pyridine in here, and then that's how you make the reaction go. So that'll be an extra step. It's unlike the hydrolysis of acid chlorides or the synthesis of anhydrides. This one you do need pyridine as an extra reagent. Okay, let's see that acid scavenger in action. Let's see the mechanism. Start with the acid chloride. Bring in the alcohol. And how does it begin? Bump up the pi bond. Lone pair on the alcohol. This nucleophile that attacks the carbonyl group. Double bond oxygen is now single bonded with a negative charge, extra lone pair. I still got the chlorine. You know what? Let's just be consistent. Put it over here. And then over here we have the alcohol that hangs on to all of its atoms in the first step. Lone pair just attaches it, gives 3 bonds to oxygen. Okay. Next step, bring down the pi bond. Bring back the pi bond. Bring the lone pair down. Reform it. Kick out carbon? Nope. Kick out chlorine? Yes. Kick out this group? Sometimes. Kick out this bond, the alcohol reforms, or we just reverse it. But chloride, you leave because you're a good leaving group. Nice stable anion that's not a base. Okay, this stays here. And then Cl minus. Okay, I'm putting this part in parentheses. Double parentheses, meaning don't include this in your mechanism. But I wanted to explain the acid scavenger part. Let's say you set up the lab, you're in the lab, you set up the experiment, and you forget to add the pyridine or some other base. So in the homework, I think there's one problem that instead of pyridine, they decided to use a little sodium hydroxide. Not my recommendation, because sodium hydroxide can do hydrolysis of acid chlorides. Go back to the beginning of this video, and NaOH reacts with acid chlorides. But anyways, if you forget to add any type of base, you just mix the alcohol and the acid chloride, then in your cleanup step, what's the reagent that removes the H+? It's the alcohol. And so this lone pair will pick up the H plus, and now the alcohol can't do the step 1 here. Now remember, you have to think about actually being in lab, working with a round bottom flask or a beaker, it's usually a round bottom flask, with not one molecule of the alcohol or one molecule of the acid chloride, but Avogadro's number, right? So you have a whole bunch of these molecules, acid chlorides, and a whole bunch of the alcohols. And if you could watch the molecules react, at some point these two are going to collide, and not everybody pairs up and immediately collides. As these molecules are diffusing and bouncing around solution, maybe one acid chloride molecule, another alcohol collide, go to this point, and then some other alcohol molecule says, "Oh, I'll pick up that H plus." But now, when there's an H plus on the alcohol, there's a positive charge on this oxygen. And yeah, it does have one more lone pair, but the whole purpose of this reacting is that opposites attract. This carbon of the acid chloride is very positive, not a full carbocation, but it has 2 electronegative atoms attached to it. So the chlorine's pulling away, the oxygen's pulling away. That creates a significant positive charge that draws in the negative lone pair. But if H plus attacks the lone pair first, then it kills this nucleophile. It's just dead in the water. And so the alcohol all the alcohol molecules that are supposed to work on the acid chloride are not available because they're bound up by all the acid that's being created in this step. So you got to bring in a little pyridine. Pyridine structure, it looks like benzene, but you substitute 1 carbon with a nitrogen. And the nitrogen's lone pair, not one of the Huckel numbers, not needed to get to the Huckel number of pi electrons. It's available to remove the H plus. So then you can create your ester. You got the pyridine molecule, attach a hydrogen, it puts a positive charge on nitrogen, doesn't matter. And then there's a chloride. And then these pair up, cation, anion forms a salt. You can do an extraction in the lab to rinse this away to get your ester here. That's how you might purify it in the lab. Cool. Oh, 3 reactions done. What else can you do with an acid chloride? You can make an amide out of it. One of the other carboxylic acid derivatives. Start with the acid chloride, and we want to form an amide. Well, which one would you like? Well, how about a primary one to start? Okay. In that case, you're going to use ammonia as your reagent, right? So what's the missing atoms? You need to pull off a chlorine and put on NH2. Well, start with NH3. That's more stable, less reactive. Yeah. And then we're going to technically use 2 equivalents or an excess of the amine. You don't have to include that when you're filling in the reagents, right? The organic chemist usually doesn't balance their reactions, their chemical equations. We just assume that whatever reagent you're supplying, you're using enough of it to get the job done. So in this case, we'll see in the mechanism, you need 2 equivalents. That creates a primary. If you want a secondary amide, secondary amide would have 2 carbons, 2 sets of carbons on this nitrogen, the carbonyl group, and whatever group we have one over here. So in that case, your nitrogen, that's your reagent, must have had the ethyl group already. And you're going to use a primary amine. And we're going to use an excess of it so that we get our secondary amine. This is a primary amine. Oh wait, let's do it up here. And then if you want a tertiary amide, pair of cyclohexane rings maybe, then your nitrogen had to start out with a pair of cyclohexane rings on it, or benzene. and 1 hydrogen. Nitrogen likes 3 bonds, and use an excess of that. Now, this molecule is getting pretty complicated, so maybe it's kind of expensive. So maybe you want 1 equivalent of this, and then you can bring in another base. I don't have it here. Never mind. Just use 2 equivalents. Although I don't think in the homework, but in the lab, you might see someone add some sodium hydroxide here, or pyridine. So if you see that variation on the internet, just realize, okay, someone was trying to save some money, and instead of having 2 equivalents, they use 1 equivalent of this, and they added a cheaper base, an acid scavenger, to help the reaction go to completion. Yeah. Okay, mechanism. Oh, wait, one idea. If we start with a tertiary carbon on a nitrogen, this nitrogen is primary, the carbon is tertiary. And then when you make the amide, the nitrogen is still going to have that butyl group, but the nitrogen is secondary now. So when we're classifying the amide, it's just a mistake I see from time to time by students. They think, oh, if I want a tertiary amide, yeah, if I want to create a tertiary amide, I need a carbon that's tertiary. No, no, no. The nitrogen has to be tertiary. So this nitrogen starts out secondary, and afterwards, the nitrogen is then connected to 1, 2, 3 carbons directly. That makes it a tertiary amide. Okay, cool. Let's see the mechanism. Nice. What's it going to look like? Bump up the pi bond, bring the pi bond back down. Got your acid chloride, and let's just do it with ammonia. It could be any of the nitrogen-bearing compounds. Ammonia, there it is. You could use ammonia, a primary amine, or a secondary amine. And then you get primary, secondary, and tertiary amides. Now, step 1 is bump up the pi bond, but it's also somebody with a lone pair, the nucleophile. And we should still remember that SN2 reactions is where we were introduced to nucleophiles. What makes a good nucleophile? Strong bases and SN2. Good nucleophiles are strong bases and SN2, where the S and N stand for sulfur and nitrogen. So now this is a very powerful reaction. Exothermic, watch out. It's going to heat up. You got a good nucleophile and a very reactive acid chloride. And so it quickly bumps up the pi bond. We get our tetrahedral intermediate again. Pi bond, you come back down. And kick out carbon? No. Makes a strong base. Kick out the ammonia? Yes, that can happen. It can reverse. But it's a better idea to kick out the chloride. Because then we can make the amide, which, if you remember from the previous video, the reactivity of the carboxylic acid derivatives is acid chlorides are most reactive, anhydrides, esters, and then amides are the least reactive or most stable. Or in other words, nature would prefer, out of those 4, she would prefer to make the amide because that's the most stable functional group of those 4. Okay, so when we kick out the chlorine, the nitrogen still holds 3 hydrogens, its original 3. It's making 4 bonds, has a positive charge. Oh, some of you may have said, wait, don't the opposites attract? And can't chlorine, with its 4 lone pairs, pull off the H+? No. What is that action called if somebody pulls off H+? If you accept an H+, that makes you a base. And chloride ion is not a base. Add some salt, sodium chloride to water, measure the pH. Does it become basic? No. Chloride ions are not basic. So you can't use a lone pair on the chloride. You have to have another base. And that's what we'll see in the lab. If you forget to add enough ammonia in this case, a second equivalent to serve as a base, then the yields are low. Okay, so another ammonia molecule has to come along and remove that H plus to create your primary amide. Whoops, I'll put the N here then. Nitrogen had 3, now it has 4. That's the ammonium ion. Chloride's over here. Yeah, this molecule becomes ammonium chloride, a very stable salt. And again, this second ammonia molecule is the acid scavenger. It's picking up the H plus that's being created as a byproduct of the reaction. Okay, what else can you do with acid chlorides? There's a really fun meme I put in the assignment for, on Canvas where it shows Darth Vader taking out all these rebel warriors and stuff in Star Wars. Anyway, take a look at that. The message is pretty clear. Lithium aluminum hydride can react with a lot of functional groups, including acid chlorides. When you use lithium aluminum hydride, a strong reducing agent, we're always going to have a step 2 reaction, a second reaction using hydronium ion. Lithium aluminum hydride in itself is a powerful base, and the products immediately following the reaction of lithium aluminum hydride will have negative charges. They will be basic, and we'll have to neutralize them. Just like the Grignard reactions, we always had a reaction 2 with hydronium. Sodium borohydride, same thing, almost always. I think there's an exception somewhere where we, most of the time we have H3O+. So just kind of keep them hand in hand, first reaction, second reaction. What happens? Hydride ion, H hydride ion, there it is, hydride ion, H minus is your nucleophile. We're going to bump the pi bond or simply do a substitution reaction with that. So if you substitute the chlorine with the hydrogen, you're going to make an aldehyde. Yay. I'm putting that in parentheses because that's not your final product, right? Lithium aluminum hydride reacts with aldehydes, and there's 4 hydrogens, more than enough to get the job done. This reacts again to make an alcohol. So where the double bond used to be, now you have the alcohol. Cool. Let me make sure I'm not missing anything in my notes. Nope. Time for the mechanism. What do you think might happen? Well, if we use a shortcut of beginning, not with lithium aluminum hydride, but with H minus, the mechanism follows the same exact pattern. Hey, chemistry majors, if you go on the grad school or maybe when you transfer for your college, your instructors might introduce the actual mechanism and show you the mechanism where aluminum shows up in the mechanism. I've chosen not to because a lot of organic textbooks employ this shortcut. So I'm kind of consistent with them, but it's not entirely accurate. Given that, here it is, lone pair of the hydride, go bump up the pi bond. Again, this is a powerful reaction. Hydride is a very reactive nucleophile, strong base in its own right. Acid chloride, very reactive molecule. Negative charged oxygen, gonna have the chlorine, and we have a hydrogen. So lone pair, come right back down, reform the pi bond. Okay, you're gonna kick out carbon? You're gonna kick out hydrogen? No to both. To do so or create powerful bases. H says, no, let's make stable things. Chloride comes out. This one's not reversible. Just because the chloride is gonna come out before the hydrogen or the carbon. All right, so what we get? We get an aldehyde. That's not an aldehyde. Chlorine, what'd you do? Now it's an aldehyde, sorry. Lone pair comes down, the chlorine leaves. Make a double bond O with the H on that side, and chloride is here. And then there's another equivalent of hydride from lithium aluminum hydride that bumps up the pi bond. You've seen this mechanism before. We get to the tetrahedral intermediate. Maybe you're in the pattern of, oh, bump up pi bond, bring it back down. And if you think about bringing this back down, then you have to kick out a carbon, a hydrogen, or a hydrogen. Ooh, and all three of those are powerful bases. And they says, wait, what? No, we're not doing that. We're dead. Done. This is the most stable thing so far. And you come along the lab and say, well, I don't want this negatively charged. So once the reaction is all done, let's start a new reaction by adding some hydronium ion. Now in the lab, you can't mix these two together because like I said before, lithium aluminum hydride is a strong base. And if you add the acid too soon, this base reacts with the acid and it won't have a chance to react with the acid chloride first. Okay, but we're just going to clean it up at the end, neutralize our charges, acid-base reaction here. And we're done. We made the primary alcohol. Cool. What else we got? Grignard. Yeah, Grignards react with acid chlorides too. These are all acyl substitution reactions, nucleophilic acyl substitution reactions. So maybe we're going to have the methyl Grignard come in. Every Grignard is always going to have a reaction number 2 with an acid. Substitution, well, out goes the chlorine, in comes the methyl. So you might say, ooh, that looks like a ketone. Yeah, but we're going to put that in parentheses because Grignards react with ketones. So we actually get a second Grignard molecule reacting with the ketone, and we're going to get an alcohol. This time it's going to be tertiary. Nice. Double check and make sure I don't have any. No, that's it. What should we do next? The mechanism. Although these bullet points are kind of nice for me too. If you're doing a Grignard reaction, watch out for limitations, right? So on the methyl, or if there's a long chain or a benzene ring, can't put any other groups that are acidic, like an alcohol group or an amine that has a hydrogen. Nope. Also, you can't have your Grignard reagent that possesses a C double bond O, a carbonyl group, aldehyde, ketone, acid chloride. No, because Grignard would then react with its twin, another Grignard. Yeah, so remember those limitations. All right, see the mechanism. We've seen it before. If you had an ester reacting, mechanism similar to the mechanism, there it is. The mechanism is extremely similar to the mechanism of Grignard reactions with esters. So go back to the video associated with Unit 1, Part 4 of our key concepts. Or keep rolling the video. Here's that mechanism. Okay, so we're going to bring in the Grignard. And you have the choice of showing the resonance structure of the Grignard. So instead of a covalent bond connecting magnesium to carbon, we can say, well, maybe it's ionic. I think we've mentioned before that experimental evidence suggests it is a covalent bond. But metal, magnesium, with a non-metal, carbon, are usually, those metal with non-metals are usually ionic bonds. And the mechanism kind of makes sense. The lone pair is now your nucleophile, so it can bump up the pi bond. These two dots are contained in this line right here, right? One line equals 2 dots in Lewis dot structures. So you can draw your mechanism with the covalent form if you want, or you can start your curved arrow at this lone pair if you decide to draw the Grignard as a resonance structure showing ionic bonds. bumped up the pi bond. What remains of the acid chloride is here. And then carbon is the one holding on to this pair of electrons. You get a methyl group here. Second step, pi bond comes right back. You're going to kick out a carbon with a negative charge, carbon with negative charge. No, we're not. Nature says no to that. Kick out chlorine, because the chlorine can deal with that negative charge so much better than carbon. And then we have our ketone. But then we're doing this in a round bound flask. There are more than one Grignard molecule, so remember to use 2 equivalents so you can get to the final product in high yield. Grignard reagent, a second Grignard reagent is going to bump up the pi bond. Get to our tetrahedral intermediate. Oh, if you're wondering where the MGBR went, it's up here. If you want to draw an MGBR. And then when the pi bond comes back down, the MGBR will associate with the Cl-. I have been tracking these spectator ions, so you don't have to. Let's see, am I done here? Yeah. Okay, so then you think about bringing down the pi bond, because that's a pattern. But wait, it won't work here. If you try to make a double bond, that'll give this bond, carbon 5 bonds. No, they'll then have to kick out one of the methyl groups. That'll have to carry off that bond as a lone pair. Ew, negatively charged carbon isn't going to happen. So it's dead here at the end of the Grignard. And then the molecules just sit there, be all content until you add some hydronium ion in reaction number 2. And then the lone pair on that negatively charged oxygen will say, ooh, thank you. Let me go have that H+. And we'll make our alcohol. And then hydronium turns into water. Gee, this whole mechanism looks really familiar. Yeah, the lithium aluminum hydride mechanism was exactly the same, except different reagents. Same exact use of curved arrows, though. So that's convenience. Once you start seeing the pattern, apply it to different reactions, and you got lots of mechanisms memorized. Yeah, no one mechanism, you got them all. Gilman reagent also reacts with acid chlorides. Let's see. Oh, we already saw this. This is a review. So there's no mechanism on the exam. I bet you could write it out if you needed to. I'm just putting it back in here just to make it complete. Let's just list all the reactions we need to know for acid chlorides. Back in Unit 2, we had a method of making ketones with Gilman reagents. So the Gilman reagent is nicknamed the Cooley reagent, right? C-U-L-I. And then the methyl group bumps that up. And then the chloride comes out. And then the copper somehow coordinates with that, makes it stable. We didn't talk about the mechanism, but this one does stop at the ketone. So if you wanted a ketone, Grignard can't give it to you, but the Gilman, the Corey House reagent, can. No mechanism. Nice. Ooh, we are done with the acid chloride reactions. I like numbers. So 7's the number. There's 7 reactions that acid chlorides can do. And then we start over with another derivative of a carboxylic acid. Okay, but so if some of you are saying, oh no, is there another 7 reaction? 7 reactions? And the answer is no. Acid chlorides are the most reactive. They have the most number of reactions. Then it's anhydride that's less reactive, then esters, then amides. By the time we see amides, there's only a couple reactions because they're so stable. So acid anhydrides are less reactive. They're more stable than acid chlorides. They have fewer reactions. but they all have the same mechanism, at least a similar pattern. Okay, so let's kind of take them in the same order we saw acid chlorides. First one we did was hydrolyze the acid chloride. So you can hydrolyze the anhydride. Turns out anhydrides are reactive enough to just react with water, although it is slower. So in the lab, if you want to speed it up, it's a good idea to either use an acid or a base catalyst. But you don't have to. If someone leaves the bottle open on a bottle of anhydride, it's going to start decomposing through hydrolysis. It'll react with moisture in the air, humidity. Don't breathe on it. A lot of moisture in your breath too, and that can react with the anhydride, but it is a slower reaction. Okay. The anhydride has 2 double bond O groups. I'm going to pick the one on the left, but in lab, nature picks either side. Okay, so the water molecule is going to attack, I'm going to say the left side, bump up the pi bond, bring it down, and then the anion of carboxylic acid will be the leaving group, and this will substitute with it. It's a nucleophilic acyl substitution reaction. Swap out the water with this side of the anhydride, and we're going to produce a carboxylic acid. Same thing if you use hydronium. Same thing if you use water. That is basic. And again, we're making carboxylic acid, so it's not a useful reaction for synthesis. Instead, for the chemists in the laboratory, this is, if you know this reaction, then if you want to use an anhydride, make sure your glassware, the round bottom flask, is dry. If you use a pipette, make sure you get a clean, dry one. Don't reuse one you rinsed out with water. Isn't that funny? If you rinse something, you use soap and water and you rinse it out, you think it's clean, free of contamination. But in organic chemistry, water is a reagent. It's a contaminant. Yeah, so if you rinse it with water, you've actually made it dirty. The water then can react with the anhydride. Maybe that's not the reaction you want. It's usually not. But if it happens, we can draw a mechanism for it. And hey, let me double check. I think, yeah, let's use a mixed anhydride in our example. And you can use the acid or the base, but just neutral water works too. Okay, if you have to deal with a mixed anhydride, now the carbonyl groups, the C double bond O groups, react differently from each other, right? What's happening in this first step? The weak nucleophile needs to bump up a pi bond. That's kind of like an SN2 reaction. It's definitely a nucleophilic attack. So which one is easier to attack? The less crowded. It's like an SN2. It's not SN2 though. What kind of resembles it? It's going to go after this one. No, not this one. This one has some crowding. There's a branch here. Okay, so it'll be the one on the left in this case. So if you have a mixed anhydride, have your nucleophile in the mechanism attack the side that's less crowded. Then what happens? Well, the left side gets bumped up, get a negatively charged oxygen, draw the rest of the anhydride. The right side has nothing associated with it. That arrow is not there. But over here on the left, we added a water molecule, which now has 3 bonds, positive charge. Here's our tetrahedral intermediate. What do we do with it? Bring down the pi bond and kick it out. Now, here's the turning point. If you research this mechanism online, you might see an alternate mechanism. And if you use that alternate mechanism on the exam, I will give you full credit. But this is the one I advocate because this pattern looks the same as the other mechanisms we've been seeing. So here we go. Bring down the lone pair. This carbon says, whoa, can't make 5 bonds, and I'm not kicking out this carbon. Well, maybe you're going to kick out the water molecule. So yes, it can reverse. You can also kick out this bond, and that's what's going to happen in my mechanism here. So the water molecule, I just put the H's on the right-hand side, stays attached to this carbon. This oxygen then takes on this extra 2 electrons in the covalent bond to give it a lone pair, a negative charge. Now, this molecule is less stable in water. So there are some mechanisms that say, hey, before this step, maybe the lone pair on this oxygen grabs H plus and takes that on. So if you do that step, I will give you full credit because it kind of makes sense. But this is the pattern we've seen in all the other acid chloride reactions. Bump up the pi bond and immediately it comes back. So it makes sense to just keep applying the same pattern. And now we need a cleanup step. Hey, this oxygen has an extra H plus. Oh wait, there's a weak base right over here. So hey base, why don't you pick off that hydrogen and neutralize yourself too, and then recreate 2 carboxylic acids. This molecule loses H plus. Molecule on the right, the anion of a carboxylic acid, picks up the H plus. And we have 2 carboxylic acids. It's the same, ooh, I lost some carbons. I was gonna say, it's the same carboxylic acid, you only have to draw it once, but whoops, it's not the same, right? This group, I neglected the other 2 carbons, they're still there. There we go. We actually have 2 different carboxylic acids. Yes, Dennis, you need to draw them both. Cool. Okay, synthesis of esters. Reaction 2 of anhydrides. What did I do here? I just started using symmetrical anhydrides. And if you want an ester, you need to bring an alcohol. If we're doing the acid chloride reaction, we would use pyridine. Just keep doing the same thing. If the acid chloride, which is more reactive than an anhydride, if that acid chloride reaction needed pyridine, well, the more stable anhydride is going to need it too, maybe even more so. Okay, so then we're doing substitution. So I'm going to pick the right side to leave and get substitute with the O and its carbons. So the left side carbonyl group and the right side of the alcohol connect to form our ester. And if you're tracking the carbons, this has carbons too. So we're actually going to get, I'll write as O minus, because that's probably the actual product. Let's find out by exploring the mechanism. Okay, let's bring in our nucleophile, the alcohol. What are you going to do? Bump up the pi bond. Again, if it's symmetrical, either one can react, but I'll be consistent. I'm just going to keep picking the left side. Pi bond turns into a new lone pair on the oxygen. The rest of the anhydride is still there, but to that carbon that's now tetrahedral, we attach the alcohol molecule. Step 2, bring that lone pair right back down. And again, you might see an alternate mechanism that I suggested for the previous reaction. Hydrolysis, that's the name of it. But you can proceed, just apply the same pattern, right? Bring back the pi bond, kick out this group. And now this carbon's still connected to the alcohol. Hey, alcohol still hanging on to that hydrogen. 3 bonds gives it a positive charge. And then O minus comes off with the other half of the anhydride. That's the leaving group. And now the negatively charged oxygen will react with the positively charged oxygen. And then we make our ester. Oh, wait. We have another variation here. Yeah. And then that would be, you know what, if you do this like I've done, full credit. If you're like, wait, Dennis, when we reacted with acid chlorides, we had pyridine serve as the acid scavenger. So yeah, if you decide to follow the mechanism of the acid chloride reaction, I will give you full credit because that's more likely to happen. These two actually have similar PKBs. I have to go look them up. Pyridine and acetate are both weak bases, and they might be nearly equal in their base power. I definitely have to go look it up. I don't remember. But the pyridine's been added, so it's the one that removes the H+. And that's because this carboxylic acid is still a weak acid. It can donate H+ and put the H+ back on the alcohol, and that would slow down the reaction. I am putting too many details in here. So mechanism, you decide whether you want to follow this step, pair up the ones like we did in hydrolysis, or if you want to follow the mechanism we did with acid chlorides, where the pyridine removed the H+. I'm showing it here. Either way, you make the ester. So we're all good. Ooh, I think there's just one last reaction. Let me double check. Yes. All right, 3 reactions for the anhydrides. We can make amides out of them. Start with the anhydride. And if I want to create an amide, oh, maybe I want a primary amide. Then the incoming group is NH3 is more stable. We use ammonia. If you don't want a primary amide, then bring in an amine, a primary one or a secondary one. Yeah, same pattern as acid chlorides. So primary, secondary, and tertiary amides can be made by using ammonia, like I've done here. Or you can bring in a primary amine. There's an example of a primary amine. Or a secondary amine. And then you'll get 1 more degree higher of the amide. Secondary amine, right? I think I've been using the diethylamine as an example of a secondary amine. And that's just going to put more carbons on your amide and change the degree, the classification of the amide. Last mechanism for this video. What do you think it's going to look like? Oh my goodness, you've seen it before. Let's draw, let's just do it with ammonia. But it works for any of these amines. Go bump up the pi bond, and I'll keep bump up the left side, but nature, she can choose either one, especially if it's symmetrical. Get your tetrahedral intermediate. Bring down the pi bond. Sometimes, yes, ammonia can leave, but the acetate can also leave. Whoops, acetate is leaving. And then last step or cleanup step, the base will pick that off. Now you create the acid. So if you, again, 2 options here. When we used acid chlorides to make amides, we said you had to have 2 equivalents. You do have to use, if you don't have extra base, 2 equivalents, your yields will be low, because if you show me this mechanism, I will give you full credit. The acetate is a weak base. It can remove that hydrogen to make your primary amide. And acetic acid, wait, that's an acid. That is definitely going to react with ammonia. I don't know, definitely. It'll set up an equilibrium with it and lower your yield. So you do need to add more base, a second equivalent, And some of you are going to say, wait, I already know the mechanism for acid chlorides reacting with amines, so I'll just apply that to the anhydrides. So bring in, if you decide to do that, full credit also, you bring in a second equivalent of your amine, or in this case, ammonia. And now ammonia is a weak base. It can pull off the extra hydrogen. And you'll make your amide. And the conjugate acid of whatever amine or ammonia you're using. Okay, that's enough for now. I'll see you in the next video.